Minasan, konnichiwa, Zamurai Engineer desu. In this video, we'll talk about and practice, evaluate problem solving using central divided difference approximation method while trying to observe also what will happen if we change the finite value of delta x. Okay, so that is our goal in this module. So let us proceed. Now the definition of backward difference is like this, but we are central, so actually the definition here is for the taking of limits, so it is not yet an approximation method because it has a limit, so it is a definition of what is slope. Now here it is now an approximation. Take note of the symbol f prime x is approximately equal, that is the symbol, for what? Numerator of fx plus delta x minus fx minus delta x. So meaning we add delta x and subtract delta x. Okay, so we have 2 points to consider, but instead of considering the point x, we are actually considering 2 points, which is x plus delta x and x minus delta x. And therefore, the point relevant to us is x is at the center. That's why it is called central divided difference. Okay. So as you can see in the diagram, we would like to find the slope of the curve at x, but we need 2 points for that, and the 2 points that we selected are x plus delta x and x minus delta x. Notice that if we draw a straight line tangent to the curve at x, it is having a slope almost similar to the slope of the line, straight line, with cross-section at x plus delta x and x minus delta x. So this is a straight line. Okay, so therefore we have an example again using the same rocket example. The velocity of it is given by some equation which we already memorized right now, and the valid region is still same, 0 up to 30. We need to calculate the first derivative to find the acceleration at time is equal to 16 seconds, and using a step size of 2 seconds. But now the method is central difference approximation. So going to solve this problem, we still have to what? Use 2 points wherein the point of consideration at the center. So x plus delta x, x minus delta x. This is the point wherein we want the curve to have its slope. Okay. Okay. So we have the following information: t 16, delta t 2 seconds, and you would like to solve the velocity at time is equal to 18 seconds and at time is equal to 14 seconds. So let us solve initially the velocity at 18 and velocity at 14, because we want those in order to finally solve the acceleration at 16, which is this equation. Velocity 18 minus velocity at 14 divided by 4 rather than 2. Because there are two, what? Equal delta x. 1 delta x, 2 delta x, or 2 delta x. 2 times 2 is not 4. 2 is a constant here, no? Because there are 2 delta x, and delta x is 2. So 2 times 2 is 4. Okay, so just substitute. We can find out that the approximation is equal to 29.695. You'll notice that this is very much almost the same, no? With the actual value or the calculus value of acceleration, which is actually 29.674. So 29.674, okay? So it was equal. And because of that, we can calculate the absolute relative true error by evaluating this equation, which is having a numerator of true value minus approximate value divided by true value. And you can find out that the absolute relative true error is 0.070769%. It is even less than 0.1%. So very small. It is a totally acceptable value. Okay. So any question? So this is the end of the module. Please just comment your question if you have one. Again, this is Dr. EYPEI, Teaching Engineering for Nation Building.